So a couple of interesting things. We're going to look this week at what we call wide area networks. So we've explored the internal pieces. We're going to look at how do we now connect externally. What's also interesting right now, have any of you guys heard about the term net neutrality? Yeah. And so the FCC is looking at repealing the original idea of net neutrality. And it's not quite as cut and dried as it's good or it's bad. There are models that say, you know what, repealing that is a good thing for consumers because you only would then maybe pay for the traffic that you used. But the flip side of that is there are some other issues that would arise, including that issue of free access. So you buy an internet connection, but you can only get Fox News on your internet connection. And maybe there's some bias that we can look at that way. So there are countries that have something similar to net neutrality, and there are other ones that don't. So if your internet service provider was only $20 a month, that would be good. But what if you had to pay another $5 for social media? So to get onto Facebook, well, now you got to pony up another $5.99. And if you wanted to get onto school websites, oh, there's another $4.99. So you might want to take a look at that. We're not going to directly deal with it in this class, except from the standpoint of please go out and look at it as informed voters. Make some decisions. Think about what the consequences of those. So if you have a lot of stock in telecom companies like Spectrum, maybe net neutrality is a bad thing. On the other hand, if you're purely a consumer right now, maybe it's a good thing. So we want to talk about that idea of wide area connections. What is a wide area connection? We've had LANs, we've had WANs, and so we're having all these things where we're rhyming again. But what is a WAN? What is different about it than the stuff we've looked at previously? What is the biggest difference? The reality is it's geography. The geography, that we're covering more than a small area. So we're going to look at what kind of technologies. How can I go over several different long-range areas? So one of the big differences generally is your LANs are privately owned. You own all the pieces. The WANs, you tend to go through some sort of internet service provider or network service provider. So you're probably going over through somebody like AT&T. Or here you've got Windstream. Some places you've got other options. And in fact, one of your assignments is to look at those options that you have available and see what kind of pricing you're going to have, both for you and for a business. So that geography then lets us put things distributed from remote locations to another. And so we have more terms, because if nothing else, we need a whole bunch of acronyms. And sometimes you're going to see these in the future. You need to get internet service at a corporation. You may say, oh, why did they just call something a DTE? What is this on my bill? And you know now that that's data terminal equipment. That's your customer's endpoint. And if it's a data communications equipment, that's your carrier's endpoint. So those two devices, one communicates on the WAN, so the carrier's equipment communicates over that wide area network. Your equipment communicates on the LAN. So where these two devices meet, we call a demarc, or demarcation point. And that is where their responsibility ends and yours begins. So if I look at something like this picture here, this is a WAN. So this is, here we've got Miami, we've got Houston, Detroit, New York. Those are all endpoints on a WAN. And that communicates through some means. And if, quite frankly, we may not care how that communicates. And then internally, our LAN looks like this. We have our switches, our routers, and we have that final endpoint out into that internet or across that network. So where you see that cloud, I see each one of those endpoints. And so the biggest difference in the WAN then is that geography. And so here again is that same type of terminology. Here we have our ARC equipment we own, and here we have the equipment that in most cases the carrier owns or at least provisions. You can, in some cases, buy them. So if we're talking about a cable modem or a DSL modem, you can actually buy your own. So if you've got Spectrum, and they've now cranked up, who has Spectrum in here? Somebody does. What are you paying for a modem right now? Isn't it $10 a month or something? Is it $15 a month to lease a modem? Well, here's the really interesting secret. If you don't mind using some equipment that's pre-used, you can go out on eBay and buy that same thing for $35, $40. You can buy a brand new one for $100, and quite frankly, pretty quickly, you can recoup your cost on some of that. The same way with Windstream, if you're renting a DSL modem from them, you could own that equipment. Now, the downside of that is you get hit with a lightning storm or that equipment dies, you have to replace it. But quite frankly, the reason they're willing to sell that to you at that price is they're making money off of it. And if they're up to $15 a month, that's a pretty good revenue stream for a device they're probably paying $60 for to begin with. Now, they handle the warranty then. So if you're willing to take that gamble that it's going to last longer than 4 months, you can probably get by with that. All it takes in the case of something like a cable modem is you have to call their service center and you give them that MAC address on there, and they can actually see your device plugged in. Same way with the Windstream and the DSL. Now, DSL, because there's about 400 different variants of DSL, you'll need to make sure you check with Windstream or whoever it is your provider is that you have the correct type of DSL modem. But again, you can generally buy them really, really cheaply and get better service. Quite frankly, when I had Spectrum, or before it was called Time Warner Cable, I didn't want their wireless. I wanted to be able to set up my own. And so that led me down that rabbit hole of buying my own cable modem. And there's some set standards for those. So, biggest things that are differences. So WAN versus LAN. The distance, that geography, how much traffic, and how many users. So if you think about it, Spectrum, they have to carry traffic for everybody in, say, Auburn, Tecumseh, whatever city they're serving. So they're carrying more traffic than your LAN at your business or at your home. And they're also covering some significant distance. So I'm going to kind of flip back and forth here because I think it makes more sense. We want to connect our businesses. And so our businesses now are connected, and we can purchase these services. So this is fairly typical for a business. We contract out for network services, not internet service. So only one of these buildings will actually be purchasing internet. So maybe it's this 1822 First Street, wherever it is. They're purchasing internet service. In addition, they're purchasing that T3 link, which we'll just tell you what it is here. And that T3 links to their Watertown business, then it links over to their Main Street, and then they have got a DSL connection between Madison, the two locations there in Madison. So what we're looking at here is now we're back. Notice that's that bus topology. Well, bus topology works pretty well if nothing goes wrong. We notice just from the size of it, you can think that probably that T3 line is pretty big compared to a T1 intuitively. And we know the DSL, its speeds are probably a little slower. But think about what happens anywhere in this bus topology if one of those connections gets cut, breaks, a piece of equipment fails, somebody unplugs something. So anywhere along there you have that idea of one of those could fail. So each site connects serially, so you think about that single point of failure. It does work really well. Small organizations with 3, 4, 5. The problem is it doesn't scale really well. So if you had 100 locations and they all had to connect through each other, that doesn't scale very well. So picture that same idea, but now we have 100 things in a chain. That chain breaks anywhere and we lose connection. Bus topology doesn't scale really well. What does scale a little better, and I'm going to flip to the picture of it because it makes more sense, is the idea of putting everything in a ring. And on the WAN side, which is where I came from before I came to Peru, was I built networks, fiber optic networks across the country. When we look at a ring, we know that it's got an advantage. Anything in there that gets interrupted, that ring will allow us to continue communication. So if that T3 line gets cut, the Watertown connection can still be made because we have, everything has two connections, if you want to think about it that way. So AT&T, Windstream, all of these large communication companies, CenturyLink, Level 3, whatever ones you can think of, we build, or they build these things in loops or rings so that there is redundant communication to that. So everything we do is redundant. In this particular case, we really haven't added a lot of extra expense. We've added one additional connection here. So there's a redundant T1 line going back there. So rings are an interesting way to do this. We still have to send through several connections. So, for example, if I want to get from First Street over to Main Street, it's got to go through another connection or through another connection. So if we scale this up to 100 locations, it gets a little icky. But we have redundant locations. Any site failure, it reroutes. Expansion is difficult and sometimes expensive, depending on how we have to run those redundant routes. So, in general, and I've seen them do it with a lot more than 5, but we have a limited number of sites you can put on that ring. You're not going to put 100 locations on one single ring. So we're getting closer. We're making some progress, but the reality is we're always balancing cost versus availability. So we could go to a star configuration, and a star has some advantages. So now we've got a similar setup, but now every individual site has a connection back to whatever we'll call our headquarters or whatever else you want to think about it that way. And so this has some advantage. This has some advantage, so we're not having to carry traffic for anything else. And if a connection gets severed, we lose one connection, one location. But when we look at the cost of this, so Star has a single link to each one, so we can add additional pieces fairly easily. But again, we're going to that central site. So if that central site fails, our entire WAN drops off the world. So it's got some advantages and disadvantages. As we get bigger, this might start to make some sense. Well, what makes a lot of sense is what we call a mesh. And so a mesh really is that idea of redundancy. So if you notice our full mesh, which is a little extreme up here, every site is connected to every other site. And in this case, that added a couple of extra connections. We can also do what they call a partial mesh. So here we have our most important buildings, and maybe this is a remote site. So picture something like Peru. All of our buildings are probably on a mesh, but then we have a remote site down in Auburn, and we might have a single-ended connection to that. So mesh, in other words, that multiple connections, gives us some advantage. So here's the drawback. Every WAN site connected to every other one. That's great. A lot of redundant connections. Is that cost? Most companies, unless they really have traffic that they deem that they can't go on without, aren't willing to spend this kind of money. And that's kind of unfortunate. So we also then can put together things in what we call a tiered topology. So we have sites, they're connected in rings or stars, and then we interconnect those. So We have sites that are very, very important. So let's take a look at what we're looking at here, tiered topology. So here we have very high-speed connections between a couple of different locations, and then they branch off from each one. Now, the disadvantage again, this is a way to very efficiently make some of those connections, but we have that single point of failure. So it really comes down to how much are we willing to spend. The more connections we have, the less single points of failure, the more robust our connections are. But here's kind of the problem. We've built this wonderful network. It's worked for years. Nothing's went wrong. So your boss goes, well, you know, nothing's failed. We don't need that redundant link. And we eliminate it. That's one of those karma moments where immediately somebody in a backhoe will dig up your cable and you'll be out of luck. So there's a lot of different ways we can connect them. So tiered really combines some of the other ones. And oftentimes what we'll do is you'll see that this is a small ring here. They will have connected that, or the entire thing will have some sort of a ring. We really have to look at that benefits versus cost. So where did all this come from, this ability to get these connections, though? And it really started, so we have to go back in history. We have to think about something called the PSTN, or Public Switch Network. So this is a group of, originally, that old carrier equipment. The telephone operators would switch things. So originally, this was on plain old wire. The entire telephone system, from one end of the country to the other, you could get traffic and a phone call from one spot to another. Wasn't always easy. There were sometimes some weird obstacles. But it got better and better over time, and we spent a lot of money building it. And so what happened is we have this great network of phone calls. We started realizing, you know what, we can get internet service, for example, network connections, in some way, through a modem or something else, anywhere in the world. Phone companies saw that too. And they said, oh, how can I save money? And so what you have in every town is something we call a central office, in a very large city. So if you go to Omaha, there's multiple central offices. And that's where the phone company terminates all their lines. So, for example, in Falls City, there's a building downtown that the Southeast Nebraska Phone Company, everything comes into that building. Here in Peru, there's probably a small little tiny block building somewhere you can find with a air conditioner sticking out of it. That's where all the phone lines in town terminate. If you're in Auburn, there's a building on that diagonal road that leads to the courthouse that's got that original old central office. And so originally each town had one of those, and at one point they had those operators. Now that everything's digital and it's moved, so I have been in the one recently in Falls City and looked at some of the equipment they've done. It started with a room about this size, about 24 by 36, roughly. And it was full of equipment, floor to ceiling, full of equipment. Had batteries for backup, generators. Now the entire town is switched in one rack like we have back there, one 42-space rack. So it takes more space to have all the phone lines coming in. In fact, they've all switched to fiber. So the idea of a central office still remains. All those phone lines, now replaced in a lot of cases by fiber, all come into the same. We have the same idea when you look at cable modems and you look at the cable industry. They all come back to some kind of a repository called a central office or something else similar to that. You may have remote stations, but generally in a city they'll all come back to one location. So we have a couple of terms we need to look at in here. And so one of those is something called the local loop, or we also call it the last mile. And so that is that how we connect from our business, our residence, to that central office. So the central office generally has a ton of bandwidth. They've got a big pipe going into it, if you want to think about it that way. And then how do we get that? And that's what really has been the biggest hang up in getting fast internet service in our country has been this local loop. It's expensive. If you're in Omaha or somewhere, it's expensive to build out to every business. And in fact, in Omaha, they tried something with a company that has worked out with somewhat mixed results in a few areas, where they actually had a robot that went in the sewers and would put fiber optic cable up in the sewer, at the top of sewers, because every building has a sewer going into it, right? Other companies have tried to do the same thing with gas lines and other things, trying to avoid tearing up the streets and building into there. So there is a term, and there's some other ones you're going to see, FTTP, fiber to the premises. So the ultimate goal would be to have a fiber run from that central office all the way to your house, all the way to every business. A single fiber going out there, or a pair of fibers going out there. Well, that gets expensive. And so what they've come up with is something called a passive optical network that works in a lot of cases where we have fiber cable, multiple endpoints on it. So it's still better than copper, doesn't degrade, got more speed potential. So if we look at it, this is kind of that idea of what we're looking at. So fiber to the premises. In this case, the very top one, we have fiber going from the central office all the way down to each house. Now, in a lot of cases, at some point you'll find a pedestal or some equipment out there. Usually it's green. And that generally is kind of a splitter or some way that we can then distribute to multiple residences. So there's a lot of different terms. One of the companies, Verizon, is really known for this. They come out and put in this interface, and then they use the existing copper cabling. Cable companies do something very similar. So they have what they call nodes, and so each node, so you may have 6 or 8 or 10 or 20 houses on one node, and they're all linked together into a network. So you may not have fiber from your Cablecom or Spectrum, but not too far away, they've actually got fiber to get enough bandwidth to you. So that's kind of the models we're looking at when you think about that. So there's a ton of different terms, and if you do have fiber at your house, and a lot of places do, they call them optical network units or carrier endpoints, and so they'll put a little box on your house. Now the weird thing about fiber, the copper was really great because they could put voltage on that copper, and so your old telephones, you didn't have to plug them into a wall or anything else for a power. You just plugged it into that phone jack, and you could talk on it. And if you were ever interested enough, and maybe some of you guys did this as a kid, you could take a phone cable and strip it off so you had the bare wires and stick it on your tongue and it would shock the crap out of you. It carried about 48 to 56 volts of power. That was really great. Optical, though, doesn't have that. So one of the things that ends up happening is you tend to have a little box they plug into your house that powers then this terminal at the end. The phone companies were in transition, and they needed some way, a standard that they could send data, because they started realizing, you know what, data is important, and we know that we can carry more than one phone line, and there were businesses that needed more than one phone line. So they came up with something called a T-carrier system. So originally, T-carriers, they couldn't carry more than one phone call on one phone line. And so originally you had a bundle of cables coming in, and now we figured out through something called TDM, time division multiplexing, that we could carry more calls on one phone line. Because when you get on a phone, do you talk all the time? Well, we all know one person who does. But when you get on a phone, notice all those pauses and everything? We figured out that we could put multiple phone calls on one pair of phone lines because it wasn't really that heavily used. And so we came up with this idea of time division multiplexing. So in other words, we chop that up into tiny slices. And the really great thing about T-carriers is it can go over plain old phone wire, fiber optics. It can go over wireless links. It can go over cable modems if we needed it to. We can send it over almost anything. So it's kind of this ubiquitous standard. And we said, all right, great. And it has some advantages because most businesses need phone lines. And so a T1 over here has 24 channels, or it could carry 24 phone calls at once. And originally it was 24 phone cables buried together. And that means each slice of that is 64 kilobits. So the Bell Labs and Lucent Technology, they worked a long time to figure out what the minimum bandwidth was for a phone call. And when we put it to digital, they said this is the minimum bandwidth we need for a really good phone call. And it has to do with the Nyquist frequency and how we sample, but they came up with 64 kilobits. What that did when we put those all together, you could buy a T1 for all phone, and you could get 24 phone lines. And if you think about a business, say a small hospital, they might need 24 phone lines going in and out of that hospital. There we go. We bundle in 24 into a phone system and you're good to go. But what it can also be done is that's the same as having 1.544 megabits per second. So now that doesn't seem very fast. But in the times of dial-up phone calls, and when you had to hear the screeching of the modem, that's pretty fast. The other advantage to that T-carrier is I get that bandwidth both directions. So it's 1.544 down, or 1.5 megs down, but it's also 1.5 megs back up. So I could send video and other things over it. So for a company, this was really great because I could also do 12 of these channels as voice and then get half of that then as data. And for a small business, that was pretty decent. But they also have variations of that. So if I look over here, so here's a T3. This is kind of an odd numbering system, and I'm not sure where that actually came from. But a T3 is really 28 T1s or 672 phone lines. So if I say a T3 is a big chunk of data and phone lines, and in fact, it's 45 megs per second, both directions. That's a pretty good chunk of data, even today. Again, T1s we can get anywhere. Any location in the state, I can say I need a T1 line, and we can find it. Here's what's weird about T1s. The T1 itself may not be that expensive, a couple $100 a month, which, again, sounds expensive if you're used to buying Spectrum. But if I'm a business and I need phone lines, all right, there I have a connection. But what you pay for is that local loop we said was that distance from your location to the central office. You pay for that local loop. In the case of a T-line, that local loop is probably not Auburn because Windstream doesn't have the facilities. So if I have a T1 system here, I pay local loop, for example, all the way back to Lincoln. And it can get expensive. So in 2008, I saw the bill for a T1 line that was set up, and and it was a grant-funded thing, so it wasn't costing the hospital anything. But it was a T1 for a rural health initiative that linked everybody, all these small hospitals in Nebraska, back to Lincoln to a central repository. It was a great idea. So you could send data, you could send images, and it was $4,000 a month altogether for one data line from Falls City to Lincoln. And the price was only, I think, if I remember correctly, it was $800 for the T1 line, $3,200 in local loop charges because that local loop charge is charged per mile. Now, it's grant funded, so it doesn't cost you anything, right? Well, that's really coming out of your federal tax dollars. And there were restrictions on it. One of the things, because originally when I found that, I said, well, this would be a great backup internet connection we could use for if we needed to. But by the contract, I was prohibited from sending any data through there that went out of state. And if you know where Falls City is, they're right on the border with 2 other states, and they had agreements with hospitals across the state lines, so that didn't work. In fact, we ended up redoing that and going with an alternative plan that I'll talk about, something very similar. But T1 carriers, you can get a T5. A T5 has 5,700 phone lines. If you needed 5,700 phone lines, are there customers that need 5,000 phone lines? There actually are. Think about a very large call center. They might need hundreds and hundreds of call lines. Think about somebody like Eddie Bauer. Has anybody heard of Eddie Bauer? Their call center employs thousands of employees. So we might need something that large. But if I look at it from a data pipeline, whoa, here we go, 400 megs per second. And that's dedicated. It's not a variable. I might get 400, I might not. This you're locked in at 400 megs per second. Up and down. So it's a big pipeline. But it's not cheap. You're spending thousands and thousands and thousands of dollars a month on that. But I can get it anywhere. So it's one of those things, if I'm in Ogallala, Nebraska, I know I can get a T3 if I need to. So I can set up a company in Ogallala to do software. I can make it work. So T carriers work. So we can buy pieces of one, and so that worked. It really is, and still is, a very effective system. Companies use it all the time. So T1, branch offices, T3s. So we can get a piece of one. If I have no other option, T carriers are an option. When we set up in Plattsmouth, we had a regional center there for a little bit, the college did. That was all we could get. And so we had to come up with a way to do it. So T carriers generally are set up by the company. They can do about anything. Like I said, it can go over plain wire. It can go over coaxial. It can do all different kinds of things. When I get more than a single T1 or a T3, I really want it on fiber, just for consistency and the ability to do it, but it works. Now, if I look at this, does this look very similar but different? What's different about the wiring scheme here? So we looked at in class, we looked at 568A and B. This sort of looks like B, doesn't it? But what's different? Notice that we start out with a solid color and go to a stripe. So it even uses a slightly different color scheme and wiring scheme. So you have to be careful of that. And I have ran into where phone techs weren't aware, and we ended up and we had issues with the wiring. So it's something to look at. It looks very similar. So everything looks the same except that receive pair. So you order a T1 connection, it doesn't work. Well, great. So the device you're going to look at, a lot of cases, something like this. Small connector on the wall. So they will, usually the phone company sets up everything on their point, and they give you a jack that you plug into your connector. So they also call it in some cases a CSU, DSU, channel service unit or data service unit. So sometimes we put them together. What it really does is that's the device that combines those 24 channels together or separates them out. Again, this is equipment that generally you don't have to deal with. You just order it and they have that equipped. So, for example, here we have the T carrier between these two locations. Here's our equipment, and here's our equipment at the other end. So it's not the cheapest way to get a connection between two locations, but it's very effective. The other piece that happens that's really nice about a T carrier is we own that chunk of bandwidth between there. We don't have to worry about encryption and some of those other pieces as much because it's not out on the public internet. Does that make sense? So we generally own that piece between there. So here's an example a T carrier connecting our LAN into the pieces. Well, alternatively, there was a service that used to be called ISDN. And ISDN really was a way to add data and phones as another method, and they would bond a couple phone lines together. It wasn't very fast, but again, it was something that you could get that was faster than the dial-up connections. And from that led to something that we're going to call frame relay. And one advantage to frame relay, we said, remember, connection-orientated versus connectionless. So frame relay adds some overhead that creates these circuits. So those circuits are kind of interesting. So we create a circuit. So T1, we're paying for that chunk the whole time. It's like we've bought the water pipe. Frame relay, though, frame relay is kind of interesting. So they're virtual circuits. We don't own the WAN pieces between there. But we can also determine whether we're going to have a switched or permanent. So a permanent one keeps that pipe open the entire time for our use, whether we're sending data or not. Switched only has that pipe open when we need it, and we only pay for the bandwidth that we use. So the biggest advantage is less expensive. So frame relay is another way we can communicate. And it's got the advantage of cost. T1s are still pretty pricey. Frame relay, we can get a lot cheaper. Well, now DSL has gotten to the speed and reliability that it actually is a competition for T1s. So DSL sends data at a higher frequency than what you hear over a phone line. So we alter that signal to move it up in amplitude or phase, so we have some way to send data over an existing phone line. So DSL takes already existing copper and sends it up. Now, there are probably 100 different varieties. ADSL, SDL, VDSL. Companies are coming out with new ones every minute. It's a way to leverage existing copper connections, is what it really is. So the key difference is whether you're buying symmetrical or asymmetrical. So symmetrical means it's the same both sides. So you're getting the same down as you are up. And when you look at your pricing plans, most consumer plans are asymmetrical. In other words, you get a lot more downstream data than you send up. But if I'm a business and I'm pushing a lot of data out, maybe I'm using Salesforce.com or one of the SaaS programs, I need to deal with the idea that I really push more data up than I do down. So if I do a lot of uploading, I'm doing a lot of data moving, I really need something that's symmetrical. If I'm a consumer, so if all I'm doing is sitting in my office watching Netflix videos, then I'm a consumer and I can find that I will pull more data than I will push up. So asymmetrical tends to be cheaper than symmetrical plans. So there's a lot of different pieces with DSL. So most of them require some kind of filter. So if you have DSL, when you got your little install kit, it had these filters you'd plug in your other phone lines. And what that does is keep those odd frequencies from reaching your telephone. So there are types of DSL that have to use a dedicated wire pair or multiple pairs of wires. And so there is that. The problem with most of this is the distance it can be from that central office. And it depends. The longest I've seen is about 20 to 25,000 feet. And if you think about that, that sounds, oh, that's 4.5 miles. But if you think about the way the cable has to travel on those connections and through town, in a lot of cases, it's a pretty short distance. The further you are, the slower your speed. So this particular version, ADSL2, so, it can do throughput of 24 megs downstream 3.3 upstream, but at only 1,000 or 2,000 feet. So the further you are, the way your speed goes down. Now, Windstream is carrying some newer technologies and some of the other ones that in theory allow us to send faster and faster data. So DSL is increasing, hopefully. And I have seen even in town, some people claim that they're getting 30 to 40 megs per second. So, a couple of other terms you may see. So you may see there's something called a DSLAM, Digital Subscriber Line Access Module. So that's really, if I'm here in town, that's in that little module or building or somewhere. If I'm in a neighborhood in Lincoln, they may have built a small one right outside of each neighborhood, and that's what we're connecting to. So that DSLAM has multiple connections out to those modems that are out there. So DSL has some uses. It uses existing technology. Its biggest competitor is this guy, cable. This has changed. So the latest DOCSIS standards say, hey, we can get 300, 400, 500 megs per second. And in fact, last year when I had Time Warner, I could get 30 megs downstream fairly reliably and about 1 to 2 upstream. The other problem with that is I'm sharing that bandwidth in my entire node. I don't have my own separate connection, so it's one of the downsides to broadband cable. It's available everywhere, and if it weren't for cable companies, most of us wouldn't have broadband internet. But we share that connection between several people. So, cable looks like that. They have tried to increase, part of the reason they've increased the speed is they cut out all the analog channels. So now if I plug in a television in, and it's an older television into cable, do I get anything? No. Most of the time I have to have their special device or box. And so they're trying to limit the amount of that bandwidth that's used by TV so they can maximize their data connection. So you will generally have to have some form of cable modem. There's all different kinds. Again, it's worth buying your own, quite frankly. So a couple of other terms you may see is something called HFC. In other words, there's a fiber link connected also in the same bundle as the coaxial cable. Ton of stuff in here. So I'm trying to get through it because one of the things I want to do is hopefully on Wednesday for the you guys, unfortunately we can't do it online, is I've got in some of the new parts for building some new computers for the lab. So hopefully we'll get to actually play with something. Except for Vinsky. I'm seeing he could break things quickly. So we also have something called an ATM. Not where you get your money out of. And I'll reference one of my pet peeves. Have you ever had anybody say, I'm going to go to the ATM machine? What did they really just say? I'm going to go to the automated teller machine. So, just my own personal pet peeve. So, ATM is another way we can bundle up some of our data. ATM is kind of interesting because everything else we've done, if you look at the size of it, we have variable sizes for those packets. ATM says, no, you only have 48 bytes plus a 5-byte header. So it's a fixed size, and we call it a cell. So it's an interesting way. Now we have to break down our data, so our data gets broken down into it. But it's a great way we can maximize resources because this allows us to send data. And what we actually do is we have a start and a stop. We send data in great big bursts. So if I have a couple of companies and they're all connected with ATM, one of them's not sending any data, another one is, I can maximize my resources to the one that I'm sending data on using ATM. So you generally don't see this at the residential side, but a couple of things that happens with it. So ATM has Smaller packet size, that means there's more overhead. The more times we have to break things up, each one of them has a little header, but it's very efficient because we're maximizing that. It's also very reliable, and we can also specify things like quality of service. So carriers, so companies like Frontier, Windstream, CenturyLink, like ATM, because I can specify that QoS, and so I can move things that aren't very important in their eyes. So I can put my phone calls on QoS that they're paying for, and I can move less sensitive data to slower pieces. So what are we looking at? So here we have that endpoints at our internet service provider or phone company, and so we're moving data from point to point. So it's another way we can do it. And the phone companies really kind of liked it. There's other pieces in there. One of them is I can send a huge amount of throughput. And this standard, we can actually go faster than that now. 622 megs per second. So we're getting some pretty beefy chunks of data across there. But because we break it down, because we have fairly fast integration, and we can take any kind of internet, Ethernet packets and spin them into there, it's pretty expensive. So you're not really going to see that around here a whole lot. What you do see is something called Sonnet. It's got a lot of other names, but Sonnet really says, you know what? We want a lot of fault tolerance. And we're going to get that fault tolerance really by sending synchronous paths. So remember I told you about those rings? Well, those rings work really well if they're in sync. So think about it. So everything is based on timing in Sonnet. So we sync things based on time, very fast data transfer, and what it really is, and maybe it makes more sense to look at it this way, is it really is a ring. So notice we have incoming and outgoing. So here's outgoing ring 1, there's incoming ring 1. So this is a bunch of loops to different areas. And then we are connected in a multiplexer. So Sonnet is really a collection of loops, This is probably our best connection method, quite frankly, right now. Sonnet rings. So, sounds really cool. We build these very big rings. Telecom carriers, companies like Level 3, CenturyLink, AT&T, this is how they move the bulk of their traffic, is through Sonnet rings. And part of that has to do with the speed that we can do. So if I look at what we call optical carrier, or OC levels, notice the lowest OC level. Is that faster than a T3? Yeah, T3 is only 45 megabits per second. Look at what an OC1 is, 51. I can get bigger. So now I can go, OC3 is 155 megs per second. So that's essentially the speed that we have at our campus right now. We have about an OC3. But look what I get down here. Right now in OC768, we can do 40 gigabits per second. Wow. Now, could our college afford an OC768 connection back to Lincoln? Yeah, no. But it is the fastest connection we can have. Internet service providers use it. So they move backbones. If you look at one of the weird ways we measure data is the size of the Library of Congress. You guys all know what the Library of Congress is? Every book and every article and every document ever produced is copied and stored at the Library of Congress. We could move that entire chunk of data using OC768 from Washington, D.C. to California in under 2 minutes. That's the size of that network and the speed of it. But it's expensive. So right now, if my numbers are correct, which I hope there are, we spend about $20,000 a year on internet service providers here at the college. And we have a little less than an OC3 actually in our pipeline back to Lincoln. So this is where we are headed. Now, carried over that, we have something called MPLS a lot of times. So MPLS then is another way we can handle traffic. So internet service providers use it. So mid-range providers, large providers, how they move traffic from one site to the other. So it really is a way we bundle up all that TCP packet traffic and we move it, we lump it together and we handle it with a switch, we call it. So you'll see the term MPLS. Oh. And then we have something called Metro Ethernet. Because we don't have enough different standards, we want to throw out a couple more. So Metro Ethernet, so this is kind of an interesting idea. So Metro Ethernet, so imagine you're a small town, maybe a large town, maybe you're Chicago. And wouldn't it be really handy if there was a metro network that all of the major companies could get onto and send their data from one end of the town to the other? And we're using very smart switches to form a pathway. So it's got some advantages. It's got some interesting advantages. So we already have a lot of these pieces in place. So now, if we're going to contain that traffic inside of our metro network, we can directly connect companies and kind of bypass a little bit of that overhead. So think about it from a corporate standpoint. We have streamlined connections, things we're already using. We've probably got the hardware and software to do it. So now we're going to connect onto a Metro Ethernet network. And so some cities are actually using your public dollars and saying, hey, let's connect a metro network for ourselves. Let's connect that metro network, and we're going to build one on our own. It's a great idea. Is that going to happen in Nebraska, though? Unfortunately, Nebraska, because of some laws that got passed, it's illegal for public entities to provide internet service. And so it even affects here at the college. We're a public entity, and we have issues if a resident can pick up Go Blue and actually log on in the town. So if you think, well, great, I live in Auburn, and I'd like to have free internet sponsored by the city. No, we can't do that due to some state laws. But in a lot of other areas, this is really becoming an interesting model for communications. All right, so we have a little bit left. Well, I want to look at your assignments for this week really quickly. So there is an assignment of internet troubleshooting. So your discussion board is really to do, if I can get it to go there, click along. So it is, where is week 15 and why didn't it pop to the top like it should? Here it is. So you're doing 11-2, which is a troubleshooting assignment. So we will talk a little bit about that on Wednesday. But I would look at that assignment. Some people have already started on that one. The other assignment you have, if I go back into week 15, is case 11-2. So you're doing project and case both number 2s, which is kind of weird, but just the way the book. That one is actually you're exploring the WAN options in your local environment. So what I would like for you to do is start on that one so we have a little head start and we can talk about what some of those options are on Wednesday, and hopefully that will give you guys a little bit of assistance and help on that assignment. All right, so there also is a quiz. The other piece I want to remind you about is lab connections. So when I go in, there's some people who have went through lab connections, done all of them already. They're done for the year. I can put the 300 points because they got that high of scores, and I can dump the 300 points into the gradebook now. There's other people who did week 1 and 2 and have not done anything since then, and those are not going to score so well. So remember that the lab connections, we have roughly 1,000 points in the class. Lab connections are 300 of those, so it's a big chunk. It's 30% of your grade in here. So even if you blew 4 tests out of the 16, you did all the lab connections, you can end up with a really, really great score. They're also designed that they assist you with some of the assignments and other things. So make sure you have done the lab connections and you've got those caught up. So I do not pull those out till finals week in terms of grades. So I'll set that final due date when I go in and pull grades. The other thing to remember is that percentage in lab connections lies to you, because it only gives you the percentage of the assignments that you have done. It's what they call a running total. If you have not done an assignment, it will change the percentage when I actually calculate it. So if you've done 9 assignments, you've got all hundreds on them, but there's 10 assigned and you didn't do one, your average would actually be a 90%, not 100%. So it does change those missing assignments. And there's not an easy way, because I skipped a lot of assignments, for me to do it other than just a running total. IP address. Working with Matt. All right, hang on. Let me pause this real quick. Let me send a couple of them with you because I'm not sure which one she's working out.